Calibration is a comparison between measurements one of known magnitude or correctness made or set with one device and another measurement made in as similar a way as possible with a second device. The device with the known or assigned correctness is called the standard. The second device is the unit under test, test instrument, or any of several other names for the device being calibrated. The formal definition of calibration by the International Bureau of Weights and Measures is the following: operation that, under specified conditions, in a first step, establishes a relation between the quantity values with measurement uncertainties provided by measurement standards and corresponding indications with associated measurement uncertainties and, in a second step, uses this information to establish a relation for obtaining a measurement result from an indication. History: the words calibrate and calibration entered the English language during the American Civil War, in descriptions of artillery. Many of the earliest measuring devices were intuitive and easy to conceptually validate. The term calibration probably was first associated with the precise division of linear distance and angles using a dividing engine and the measurement of gravitational mass using a weighing scale. These two forms of measurement alone and their direct derivatives supported nearly all commerce and technology development from the earliest civilizations until about AD 1800. The Industrial Revolution introduced wide-scale use of indirect measurement. The measurement of pressure was an early example of how indirect measurement was added to the existing direct measurement of the same phenomena. Before the Industrial Revolution, the most common pressure measurement device was a hydrostatic manometer, which is not practical for measuring high pressures. Eugene Bourdon fulfilled the need for high-pressure measurement with his Bourdon tube pressure gauge. In the direct reading hydrostatic manometer design on the left, an unknown applied pressure par pushes the liquid down the right side of the manometer U-tube, while a length scale next to the tube measures the pressure, reference to the other, open end of the manometer on the left side of the U-tube. The resulting height difference H is a direct measurement of the pressure or vacuum with respect to atmospheric pressure. The absence of pressure or vacuum would make H equal 0. The self-applied calibration would only require the length scale to be set to 0 at that same point. This direct measurement of pressure as a height difference depends on the density of the manometer fluid, and a calibrated means of measuring the height difference. In a Bourdon tube shown in the two views on the right, applied pressure entering from the bottom on the silver barbed pipe tries to straighten a curved tube, moving the free end of the tube that is mechanically connected to the pointer. This is indirect measurement that depends on calibration to read pressure or vacuum correctly. No self-calibration is possible, but generally the zero pressure state is correctable by the user. Even in recent times, direct measurement is used to increase confidence in the validity of the measurements. In the early days of U.S. automobile use, people wanted to see the gasoline they were about to buy in a big glass pitcher, a direct measure of volume and quality via appearance. By 1930, rotary flowmeters were accepted as indirect substitutes. A hemispheric viewing window allowed consumers to see the blade of the flowmeter turn as the gasoline was pumped. By 1970, the windows were gone and the measurement was totally indirect. Indirect measurement always involve linkages or conversions of some kind. It is seldom possible to intuitively monitor the measurement. These facts intensify the need for calibration. Most measurement techniques used today are indirect. Basic calibration process: the calibration process begins with the design of the measuring instrument that needs to be calibrated. The design has to be able to hold a calibration through its calibration interval. In other words, the design has to be capable of measurements that are within engineering tolerance, when used within the stated environmental conditions over some reasonable period of time. Having a design with these characteristics increases the likelihood of the actual measuring instruments performing as expected. The exact mechanism for assigning tolerance values varies by country and industry type. The measuring equipment manufacturer generally assigns the measurement tolerance, suggests a calibration interval and specifies the environmental range of use and storage. The using organization generally assigns the actual calibration interval, which is dependent on this specific measuring equipment's likely usage level. A very common interval in the United States for 8 to 12 hours of use 5 days per week is 6 months. That same instrument in July 24 usage would generally get a shorter interval. The assignment of calibration intervals can be a formal process based on the results of previous calibrations. The next step is defining the calibration process. The selection of a standard or standards is the most visible part of the calibration process. Ideally, the standard has less than 1/4 of the measurement uncertainty of the device being calibrated. When this goal is met, the accumulated measurement uncertainty of all of the standards involved is considered to be insignificant when the final measurement is also made with a 4:1 ratio. This ratio was probably first formalized in Handbook 52 that accompanied MILS TD 45662A, an early U.S. Department of Defense metrology program specification. It was 10:1 from its inception in the 1950s until the 1970s, when advancing technology made 10:1 impossible for most electronic measurements. Maintaining a 4:1 accuracy ratio with modern equipment is difficult. The test equipment being calibrated can be just as accurate as the working standard. If the accuracy ratio is less than 4:1, then the calibration tolerance can be reduced to compensate. When 1:1 is reached, only an exact match between the standard and the device being calibrated is a completely correct calibration. Another common method for dealing with this capability mismatch is to reduce the accuracy of the device being calibrated. For example, a gauge with 3% manufacturer-stated accuracy can be changed to 4% so that a 1% accuracy standard can be used at 4:1. If the gauge is used in an application requiring 16% accuracy, having the gauge accuracy reduced to 4% will not affect the accuracy of the final measurements. This is called a limited calibration. But if the final measurement requires 10% accuracy, then the 3% gauge never can be better than 3.31. Then perhaps adjusting the calibration tolerance for the gauge would be a better solution. If the calibration is performed at 100 units, the 1% standard would actually be anywhere between 99 and 101 units. The acceptable values of calibrations where the test equipment is at the 4:1 ratio would be 96 to 104 units, inclusive. Changing the acceptable range to 97 to 103 units would remove the potential contribution of all of the standards and preserve a 3.3:1 ratio. Continuing, a further change to the acceptable range to 98 to 102 restores more than a 4:1 final ratio. This is a simplified example. The mathematics of the example can be challenged. It is important that whatever thinking guided this process in an actual calibration be recorded and accessible. Informality contributes to tolerance stacks and other difficult to diagnose post-calibration problems. Also in the example above, ideally the calibration value of 100 units would be the best point in the gauge's range to perform a single-point calibration. It may be the manufacturer's recommendation or it may be the way similar devices are already being calibrated. Multiple point calibrations are also used. Depending on the device, a 0-unit state, the absence of the phenomenon being measured, may also be a calibration point. Or 0 may be resettable by the user. There are several variations possible. Again, the points to use during calibration should be recorded. There may be specific connection techniques between the standard and the device being calibrated that may influence the calibration. For example, in electronic calibrations involving analog phenomena, the impedance of the cable connections can directly influence the result. All of the information above is collected in a calibration procedure, which is a specific test method. These procedures capture all of the steps needed to perform a successful calibration. The manufacturer may provide one or the organization may prepare one that also captures all of the organization's other requirements. There are clearinghouses for calibration procedures such as the Government Industry Data Exchange Program in the United States. This exact process is repeated for each of the standards used until transverse standards, certified reference materials and/or natural physical constants, the measurement standards with the least uncertainty in the laboratory, are reached. This establishes the traceability of the calibration. See metrology for other factors that are considered during calibration process development. After all of this, individual instruments of the specific type discussed above can finally be calibrated. The process generally begins with a basic damage check. Some organizations such as nuclear power plants collect as-found calibration data before any routine maintenance is performed. After routine maintenance and deficiencies detected during calibration are addressed, an as-left calibration is performed. More commonly, a calibration technician is entrusted with the entire process and signs the calibration certificate, which documents the completion of a successful calibration. Calibration process success factors. The basic process outlined above is a difficult and expensive challenge. The cost for ordinary equipment support is generally about 10% of the original purchase price on a yearly basis, as a commonly accepted rule of thumb. Exotic devices such as scanning electron microscopes, gas chromatograph systems and laser interferometer devices can be even more costly to maintain. The extent of the calibration program exposes the core beliefs of the organization involved. The integrity of organization-wide calibration is easily compromised. Once this happens, the links between scientific theory, engineering practice and mass production that measurement provides can be missing from the start on new work or eventually lost on old work. The single measurement device used in the basic calibration process description above does exist. But, depending on the organization, the majority of the devices that need calibration can have several ranges and many functionalities in a single instrument. A good example is a common modern oscilloscope. There easily could be 200,000 combinations of settings to completely calibrate and limitations on how much of an all-inclusive calibration can be automated. Every organization using oscilloscopes has a wide variety of calibration approaches open to them. If a quality assurance program is in force, customers and program compliance efforts can also directly influence the calibration approach. Most oscilloscopes are capital assets that increase the value of the organization, in addition to the value of the measurements they make. The individual oscilloscopes are subject to depreciation for tax purposes over 3, 5, 10 years or some other period in countries with complex tax codes. The tax treatment of maintenance activity on those assets can bias calibration decisions. New oscilloscopes are supported by their manufacturers for at least 5 years, in general. The manufacturers can provide calibration services directly or through agents entrusted with the details of the calibration and adjustment processes. Very few organizations have only one oscilloscope. Generally, they are either absent or present in large groups. Older devices can be reserved for less demanding uses and get a limited calibration or no calibration at all. In production applications, oscilloscopes can be put in racks used only for one specific purpose. The calibration of that specific scope only has to address that purpose. This whole process is repeated for each of the basic instrument types present in the organization, such as the digital multimeter pictured below. Also, the picture above shows the extent of the integration between quality assurance and calibration. The small horizontal unbroken paper seals connecting each instrument to the rack prove that the instrument has not been removed since it was last calibrated. These seals are also used to prevent undetected access to the adjustments of the instrument. There also are labels showing the date of the last calibration and when the calibration interval dictates when the next one is needed. Some organizations also assign unique identification to each instrument to standardize the record keeping and keep track of accessories that are integral to a specific calibration condition. When the instruments being calibrated are integrated with computers, the integrated computer programs and any calibration corrections are also under control. Quality. To improve the quality of the calibration and have the results accepted by outside organizations, it is desirable for the calibration and subsequent measurements to be traceable to the internationally defined measurement units. Establishing traceability is accomplished by a formal comparison to a standard which is directly or indirectly related to national standards, international standards, or certified reference materials. This may be done by national standards laboratories operated by the government or by private firms offering metrology services. Quality management systems call for an effective metrology system which includes formal, periodic, and documented calibration of all measuring instruments. ISO 9000 and ISO 17025 standards require that these traceable actions are to a high level and set out how they can be quantified. Instrument calibration. Calibration may be called for a new instrument, after an instrument has been repaired or modified, when a specified time period has elapsed, when a specified usage has elapsed, before and or after a critical measurement, after an event, for example, after an instrument has had a shock, vibration, or has been exposed to an adverse condition which potentially may have put it out of calibration or damage it, sudden changes in weather. Whenever observations appear questionable or instrument indications do not match the output of surrogate instruments, as specified by a requirement, for example, customer specification, instrument manufacturer recommendation. In general use, calibration is often regarded as including the process of adjusting the output or indication on a measurement instrument to agree with value of the applied standard, within a specified accuracy. For example, a thermometer could be calibrated so the error of indication or the correction is determined, and adjusted so that it shows the true temperature in Celsius at specific points on the scale. This is the perception of the instrument's end user. However, very few instruments can be adjusted to exactly match the standards they are compared to. For the vast majority of calibrations, the calibration process is actually the comparison of an unknown to a known and recording the results. International. In many countries a national metrology institute will exist which will maintain primary standards of measurement which will be used to provide traceability to customers' instruments by calibration. The NMI supports the metrological infrastructure in that country by establishing an unbroken chain, from the top level of standards to an instrument used for measurement. Examples of national metrology institutes are NPL in the UK, NIST in the United States, PTB in Germany and many others. Since the Mutual Recognition Agreement was signed, it is now straightforward to take traceability from any participating NMI, and it is no longer necessary for a company to obtain traceability for measurements from the NMI of the country in which it is situated. To communicate the quality of a calibration, the calibration value is often accompanied by a traceable uncertainty statement to a stated confidence level. This is evaluated through careful uncertainty analysis. Sometimes a DFS, departure from spec, is required to operate machinery in a degraded state. Whenever this does happen, it must be in writing and authorized by a manager with the technical assistance of a calibration technician. See also. References: Crouch, Stanley and Skug, Douglas. Principles of Instrumental Analysis. Pacific Grove, Brooks Cole. ISBN 0-495-01201-7. External links: Master Calibrators Association, Industry Experts on Electrical Calibration, Adjustment and Metrology, Electrical Calibration Video which explains the relationship between calibration, traceability, accreditation with flow measuring devices.